Oberleutnant Franz Stigler felt the vibration through his control column before he heard the change in engine note. It was March 21st, 1944, over Western Germany, and his Messerschmitt Bf 109G6 was climbing hard to intercept the formation of American bombers returning from Frankfurt. He had pushed the throttle forward to the emergency power setting, demanding everything his Daimler-Benz 605 engine could give. The engine responded, initially, the supercharger whined at maximum boost. The propeller bit into the thin air at 7,000 meters. But then came the sound every German pilot dreaded, a sharp, metallic rattling from deep inside the engine. Detonation. The fuel was igniting too early in the combustion cycle, creating shock waves that hammered the piston crowns and cylinder walls with devastating force. Stigler immediately reduced throttle. The rattling subsided. He watched the American bombers, now with their fighter escorts, pull away toward the west. For Mustangs flew top cover, their distinctive profiles unmistakable even at this distance. He could not pursue, not at emergency power, not without destroying his engine. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you're watching from today. This was not the first time Stigler had experienced this limitation. Every Luftwaffe pilot knew the boundaries of what their engines could sustain. Push too hard, demand too much power for too long, and the engine would tear itself apart through detonation. The fuel simply could not support higher power settings without igniting prematurely under compression and heat. What puzzled Stigler, what troubled him and every other German fighter pilot who had engaged the Americans since late 1943, was that the American fighters seemed to have no such limitation. The Mustangs climbed away from him now, maintaining their escort formation, engines roaring at what must have been full emergency power. They had been at high power settings for the entire engagement, 20 minutes, 30 minutes, however long it took. German pilots had timed it. They had watched through gun sights and observed through binoculars. American fighters ran their engines at power settings that would destroy a German engine within minutes, and they sustained those settings for extended periods. The Americans would climb, dive, turn, climb again, all at maximum power, and their engines did not fail. They did not rattle with detonation. They simply produced power, continuously, reliably, far beyond what German engines could match. Stigler had assumed, like most of his fellow pilots, that this was a matter of engine design. American engines were perhaps built more robustly. American mechanics maintained them better. American quality control was superior. These explanations made sense. They preserved the belief that German and American aviation technology were roughly equivalent, that the difference was in execution rather than fundamental capability. But intelligence reports filtering through squadron briefing rooms in early 1944 suggested something different. The Americans were not just building better engines. They were fueling them differently. The fuel itself, the liquid that burned in the cylinders and pushed the pistons and turned propellers, was fundamentally superior to what German pilots poured into their tanks. This realization, when it came, was devastating, because fuel was not something a pilot could improve through skill or courage. Fuel was industrial chemistry. Fuel was refining capacity. Fuel was resource access and manufacturing sophistication. If the Americans had better fuel, if their fuel allowed higher power settings and longer emergency operation, then German pilots were fighting with a handicap that no amount of training or tactical brilliance could overcome. The story of how this disparity came to exist and what it meant for the men who flew and fought in the skies over Europe begins not with combat but with chemistry. German aviation fuel development in the 1930s was a triumph of synthetic chemistry born from necessity. Germany had virtually no domestic petroleum reserves. The nation that would wage mechanized warfare across Europe and aspired global power had almost no natural access to the liquid that powered modern military machines. This fundamental resource constraint shaped every aspect of German fuel development. While other nations could simply drill wells and refine crude oil, Germany had to synthesize fuel from coal through the Fischer-Tropsch process, a chemical procedure that converted coal into liquid hydrocarbons. The process was expensive, energy-intensive, and produced fuel with specific characteristics that differed from petroleum-based products. By the mid-1930s, German chemists at IG Farben and other industrial concerns had developed several grades of aviation fuel. The standard fuel for Luftwaffe fighters was designated before, with an octane rating of approximately 87. This was adequate for training aircraft and older designs. But frontline fighters required something better. C3 fuel represented the pinnacle of German aviation fuel technology. Produced through careful refining and the addition of aromatic compounds like benzene and toluene, C3 achieved an octane rating between 96 and 100, depending on the specific batch and production facility. This was a genuine achievement. German chemists had created, entirely from coal, a fuel that approached the performance of the best petroleum-based aviation fuels available in the late 1930s. The Daimler-Benz 605 engine, which powered most variants of the Messerschmitt Bf 109 from the G series onward, was designed specifically to operate on C3 fuel. The engine displaced 35.7 liters across 12 cylinders arranged in a 60-degree V configuration, with a compression ratio of 7.5 to 1. Running on C3 fuel, the engine produced 1,475 horsepower at takeoff power settings. This was impressive performance. The engine ran smoothly at combat power. It could sustain cruise settings for hours. For short periods, typically no more than 3 to 5 minutes, pilots can gauge emergency power settings that increased manifold pressure and RPM, boosting output to approximately 1,800 horsepower. But these emergency settings came with strict time limits. Exceed them, and detonation would begin. Detonation, also called engine knock or pinking, occurs when fuel ignites spontaneously under heat and pressure before the spark plug fires. Instead of a controlled flame front spreading smoothly across the combustion chamber, multiple ignition points create shock waves that collide. The result is a characteristic rattling or knocking sound, accompanied by extreme heat and pressure that can crack pistons, damage cylinder heads, and destroy an engine within minutes. Octane rating measures a fuel's resistance to detonation. Higher octane fuel can withstand greater compression and heat before igniting spontaneously. C3 fuel, at 96 to 100 octane, represented the limit of what German synthetic fuel chemistry could produce in meaningful quantities. Intelligence officers estimated that Germany's entire synthetic fuel production capacity was approximately 5.5 million tons annually by 1944, with aviation fuel comprising perhaps 20% of that total. German engineers understood the limitations. They developed supplementary systems to compensate. MW50 was a methanol water injection system that cooled intake charge temperature and reduced the likelihood of detonation, allowing brief increases in power output. GM1 used nitrous oxide injection to increase oxygen content in the intake charge at high altitude, compensating for thin air. Both systems were effective but complex, adding weight, maintenance requirements, and additional fluids to manage. Luftwaffe pilots in 1943 and early 1944 believed their fuel and engines were adequate. They had defeated Poland, France, and much of Russia with these machines. The Bf 109 and Focke-Wulf 190 had proven themselves in combat. German aviation technology was, by all accounts, world-class. Why would fuel be a limiting factor? The United States in 1944 possessed something no other nation could match: vast petroleum reserves and industrial infrastructure to refine them into specialized products at enormous scale. American fuel development did not begin with wartime necessity. It began with decades of commercial competition in the automotive and aviation industries, where engine manufacturers constantly pushed for higher performance, and fuel producers developed better products to meet that demand. By 1938, American refineries were producing aviation fuel rated at 100 octane, a significant achievement that required sophisticated refining processes, including catalytic cracking, alkylation, and the addition of tetraethyl lead as an anti-knock compound. Tetraethyl lead, a controversial additive that would later be recognized as a serious health hazard, was extraordinarily effective at raising octane ratings. Small quantities of this organometallic compound dramatically improved fuel performance. When war came, American petroleum companies and the Army Air Forces collaborated on developing even better fuels. The result was the 100-130 grade fuel designation, often shortened to 100-130. This designation required explanation because it represented a dual rating system unique to aviation fuels. The first number, 100, indicated the fuel's octane rating under lean mixture conditions, where the fuel-air ratio contained less fuel relative to air. The second number, 130, was not an octane rating at all. It was a performance number measuring the fuel's anti-knock quality under rich mixture conditions, where more fuel was present relative to air. Performance numbers above 100 indicated knock resistance superior to pure isooctane, the reference standard for the octane scale. This dual rating meant that 100-130 fuel could support significantly higher manifold pressures and power outputs when engines ran rich mixtures, which was exactly what happened during combat maneuvering and emergency power settings. The fuel literally allowed engines to produce more power than would be possible with straight 100-octane fuel. By late 1943, American refineries were producing this fuel in enormous quantities. The Bayway Refinery in New Jersey, operated by Standard Oil, could produce over 3 million gallons of 100-130 fuel per month. The refineries at Baton Rouge, Louisiana, Port Arthur, Texas, and Richmond, California, produced similar quantities.
Combined with production from dozens of other facilities, American aviation fuel output exceeded 100 million gallons monthly by mid-1944. The Packard Merlin V1650 engine, the American-built version of the British Rolls-Royce Merlin that powered the P-51 Mustang, was designed to exploit this fuel. The engine displaced 27 liters across 12 cylinders in a 60-degree V configuration. With a compression ratio of 6:1, seemingly lower than the German engines but optimized for the fuel available, the Packard Merlin produced 1,490 horsepower at military power settings. But military power was not the limit. The engine had a war emergency power setting, often abbreviated as WEP, that pushed manifold pressure to 67 inches of mercury and increased RPM to 3,000. At these settings, running on 100-130 fuel, the engine produced 1,720 horsepower. And crucially, it could sustain these settings not for 3 to 5 minutes, but for 15 minutes or more without damage. The difference was the fuel. 100-130 grade fuel resisted detonation at manifold pressures and temperatures that would destroy engines running on lower grade fuel. American pilots could engage war emergency power and maintain it through extended combat. They could climb at full power, dive at full power, turn at full power, climb again, all without fear of engine failure from detonation. This was not a small advantage. This was a fundamental disparity in capability that affected every aspect of air combat. Luftwaffe fighter pilots received thorough training on engine management at flight schools throughout Germany and occupied territories. The curriculum included detailed instruction on power settings, their purposes, and their limitations. Student pilots learned these settings through repetition until they became automatic responses. Normal cruise power for the Daimler-Benz 605 was set at 2,300 RPM with manifold pressure at 1.2 ATA, or atmospheres absolute. This setting produced approximately 1,000 horsepower and could be maintained indefinitely during patrol or transit flights. Fuel consumption at cruise power was approximately 400 liters per hour. Combat power increased RPM to 2,600 and manifold pressure to 1.3 ATA, producing approximately 1,300 horsepower. Pilots could maintain combat power for 30 minutes, the expected duration of most engagements. Fuel consumption rose to 480 liters per hour at this setting. Emergency power, the absolute maximum, pushed RPM to 2,800 and manifold pressure to 1.42 ATA. This produced approximately 1,800 horsepower. But the restriction was absolute and emphasized repeatedly during training. Emergency power could only be used for 3 to 5 minutes. Not 6 minutes. Not 10 minutes. 3 to 5 minutes, maximum, then pilots must reduce power or risk catastrophic engine failure through detonation. Instructors drilled this limitation into every student. They explained the chemistry. They showed photographs of destroyed engines, pistons cracked by detonation, cylinder heads warped by excessive heat. They told stories of pilots who exceeded time limits and had engines seize in mid-flight, leaving them to glide home if they were lucky, or bail out over enemy territory if they were not. This training created a mental framework that German pilots carried into combat. They knew exactly how long they could sustain maximum power. They monitored their chronometers. 3 minutes at emergency power to climb for altitude advantage. 2 minutes to close with enemy bombers. 4 minutes during a desperate defensive turn. Always counting. Always watching the clock. Always knowing that time was limited and the penalty for exceeding limits was mechanical death. American pilots received different training because they operated under different constraints. Flight training for P-51 pilots at bases throughout the United States included instruction on the war emergency power setting, but the emphasis was different. WEP was not a last resort desperation measure to be used for minutes and then abandoned. It was a combat tool available for extended periods. Training documents from the 56th Fighter Group, which converted to P-51s in late 1943, specified that war emergency power could be maintained for up to 15 minutes continuously. Some technical orders suggested even longer durations were permissible with proper engine monitoring. Pilots learned to engage WEP at the start of combat and maintain it throughout the engagement. The fuel made this possible. 130 fuel-resisted detonation at the high manifold pressures WEP demanded. At 67 inches of mercury and 3,000 RPM, the Packard Merlin produced 1,720 horsepower. More importantly, it produced this power reliably, without the rattling detonation that plagued German engines pushed beyond their fuel's capability. The tactical implications were profound. A P-51 pilot could spot enemy aircraft, engage WEP, climb to intercept, fight for 10 or 12 minutes at full power, and still have reserve capacity. A German pilot in a Bf-109 had 3 to 5 minutes at maximum power, then had to reduce throttle or risk engine failure.
In a turning fight, this meant the American pilot could maintain tighter turns longer because power determines turn rate and radius. In a climbing fight, the American could maintain climb power, while the German had to reduce. In a pursuit, the American could chase at full power while the German, if being pursued, could only run at emergency power for minutes before having to throttle back. Hauptmann Heinz Bahr engaged the formation of P-51 Mustangs on February 24, 1944, during an American bomber raid on Schweinfurt. Bahr was not a novice. He had flown combat missions since 1940 and accumulated over 220 confirmed aerial victories. He understood air combat, understood the capabilities of his aircraft, and understood the tactical principles that govern fighter engagements. His Bf-109 G6 was in excellent mechanical condition. The engine had been recently overhauled. The aircraft was loaded with ammunition and carried a full fuel load. Bahr climbed to intercept position at 6,500 meters, positioning his staffel between the bombers and their fighter escort. Standard tactics: execute the attack, destroy 1 or 2 bombers if possible, then disengage before the escorts could react. But the Mustangs reacted immediately. 4 P-51s from the 357th Fighter Group broke formation and turned to engage. Bahr saw them coming, judged their positions and speed, and initiated a climbing turn to gain altitude advantage. He pushed his throttle to emergency power. The Daimler-Benz responded, supercharger whining, propeller biting air, acceleration pushing him back into his seat. He climbed. 1 minute, 2 minutes. The Mustangs climbed with him, matching his rate. Staying in pursuit. 3 minutes. Bahr checked his chronometer. He was approaching the emergency power time limit. The Mustangs were still climbing at the same rate, engines roaring at what must have been full power. For minutes, Bahr had to reduce throttle. He pulled back to combat power. The climb rate decreased immediately. The Mustangs closed the distance. They were still climbing at full power. Bahr could hear their engines, could see the exhaust stacks glowing, could judge their speed by how quickly they covered the intervening distance. 5 minutes. 6 minutes. They had been at maximum power for over 6 minutes continuously, and their engines showed no signs of distress, no reduction in performance, no mechanical failure. If you find the story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. WWII, using gravity to increase speed, then pulled up into another climb. The Mustangs followed. He tried a series of tight turns, hoping to use the Bf-109's excellent turn rate to gain position. But tight turns required power to maintain, and his power was limited. The Mustangs stayed with him, their pilots keeping engines at full power through the entire maneuver sequence. 8 minutes since the engagement began. 10 minutes. The Mustangs had been at maximum power for the entire fight. Barr's tactical options were exhausted. He could not outclimb them because his emergency power time was expired. He could not outturn them because maintaining turn rate required power he could no longer sustain. He could not outrun them in level flight because their engines produced more horsepower than his. He dove for the deck, using altitude to build speed, and headed east at low level where the Mustangs would be reluctant to follow deep into German territory. The escorts broke off, returning to their bombers. Barr flew home with fuel nearly exhausted and questions multiplying in his mind. How were the Americans sustaining maximum power for 10 minutes or more? Were their engines so superior that they could operate at settings that would destroy German engines? Or was something else involved, some factor beyond engine design, some advantage that German intelligence had not identified or understood? Back at base, Barr discussed the engagement with his squadron technical officer. They reviewed engine specifications, performance charts, power settings. The numbers did not explain what Barr had witnessed. German engines should have been competitive with American engines. Both were liquid-cooled V12 designs. Both used superchargers. Both produced similar horsepower at normal ratings. Yet in combat, the American aircraft demonstrated sustained high-power performance that German aircraft could not match. Similar reports arrived from other Luftwaffe units throughout February and March of 1944. Pilots from JG-3, JG-11, JG-26, and JG-54 all described identical experiences. American fighters, particularly the P-51 Mustang, could maintain maximum power settings far longer than German aircraft. The advantage was consistent, reproducible, and decisive. Major Gunther Rahl, who commanded JG-300, ordered his pilots to time American engine performance during engagements. The results were documented in squadron records. American fighters routinely maintained what appeared to be full power for 15 to 20 minutes during combat. Some pilots reported observing continuous high-power operation for 30 minutes or more during extended running battles. This was impossible according to German understanding of engine technology. No engine could sustain maximum manifold pressure and RPM for such durations without damage. Yet the Americans did exactly that. Engagement after engagement, day after day, their engines did not fail. Their aircraft did not fall from the sky with seized engines. They simply performed continuously and reliably at power levels German pilots could only dream of maintaining. Luftwaffe technical intelligence officers began investigating. They examined crashed P-51 airframes recovered from German territory. They measured engine components, analyzed metallurgy, studied supercharger design. The Packard Merlin was a good engine, well built with quality materials, but it was not radically superior to the Daimler-Benz 605 in fundamental design. The cylinder displacement was actually smaller. The compression ratio was lower. The construction was conventional. Some intelligence analysts suggested the Americans had developed exotic metals or revolutionary cooling systems. Others proposed that American engines were simply built to looser tolerances that allowed them to withstand higher stresses. None of these explanations satisfied the evidence. The performance disparity was too consistent and too large to be explained by minor design variations. The answer, when it finally emerged through intelligence sources and captured documents, was simultaneously obvious and devastating. The Americans were not using superior engines. They were using superior fuel. The fuel itself, the liquid that burned in the cylinders, had performance characteristics that German fuel could not match. 100-130 grade fuel allowed manifold pressures and combustion temperatures that would cause immediate detonation in engines running C3 fuel. The performance number of 130 under rich mixture conditions meant the fuel could support power outputs far beyond what 100 octane alone would permit. This was not a small incremental advantage. This was a fundamental capability gap that affected every aspect of air combat. German test pilots who later flew captured P-51 aircraft confirmed what intelligence had suggested. Running on C3 fuel, the standard German aviation gasoline, the Packard Merlin produced good power at normal settings, but could not sustain war emergency power for more than a few minutes before detonation began. The engine rattled, temperatures spiked, and damage was imminent. But running on American 100-130 fuel, the same engine could sustain WEP for 15 minutes or more without any signs of detonation or distress. The fuel was the difference. Not pilot skill, not engine design, not maintenance quality. The fuel. And fuel was not something that could be addressed through training or tactical innovation. Fuel was industrial chemistry operating at a scale Germany could not match. American refineries produced 100-130 grade fuel in quantities measured in millions of gallons monthly. German synthetic fuel plants struggled to produce enough C3 to meet basic operational requirements. Luftwaffe pilots absorbed this information with a mixture of anger, resignation, and grim understanding. They were fighting at a disadvantage that was built into the fuel tanks of every aircraft they flew. Before they even started engines, before they took off, before they climbed altitude, they were already behind. The Americans had more power available for longer durations whenever they needed it. German engineers understood the fuel disparity by mid-1944 and worked to develop compensatory systems that might narrow the performance gap. The solutions they devised were ingenious, technically sophisticated, and ultimately insufficient to overcome the fundamental chemical advantage American fuel provided. MW50, short for methanol Wasser 50%, was a water methanol injection system installed on late production Bf 109 G10 variants and Focke-Wulf 190D9 aircraft. The system injected a 50-50 mixture of methanol and water into the supercharger intake when pilots engaged emergency boost. The liquid mixture cooled the intake charge temperature by approximately 70 degrees Celsius through evaporative cooling. Cooler intake temperatures reduced the likelihood of detonation, allowing manifold pressure to increase from 1.42 ATA to 1.8 ATA for brief periods. This boost increased power output from 1,800 horsepower to approximately 2,000 horsepower on the Daimler-Benz 605D engine. The performance increase was genuine and tactically significant, but MW50 came with severe limitations. The methanol water tank held only 30 liters, enough for approximately 10 to 12 minutes of operation. Once exhausted, the system was inoperative until the aircraft returned to base and ground crews refilled the tank. The system added weight, approximately 45 kilograms when fully loaded, and complexity. Additional plumbing, pumps, and control mechanisms required maintenance and created new failure points. More critically, methanol was a strategic material that Germany struggled to produce in adequate quantities. Chemical plants synthesized methanol from coal gas through energy-intensive processes. Production competed with other chemical priorities, including explosives, synthetic rubber, and pharmaceuticals. By late 1944, methanol supplies were so constrained that many Luftwaffe units could not keep their MW50 systems fully operational. Aircraft sat grounded with empty methanol tanks, waiting for supplies that never arrived. GM-1, Goring Mischung-1, was an even more exotic system using nitrous oxide injection at high altitude. The system stored liquid nitrous oxide under pressure in armored tanks installed in the fuselage. When activated above 6,000 meters, the system injected nitrous oxide into the supercharger intake, increasing oxygen content in the air mixture and allowing more fuel to burn despite thin atmosphere. The performance gains at high altitude were substantial. Aircraft using GM-1 could maintain combat power at altitudes where normally aspirated engines would lose significant power due to low air density. Focke-Wulf 198 and Bf 109 G6 variants, equipped with GM-1, could fight effectively at 9,000 to 10,000 meters, altitudes where American bombers cruised. But GM-1 shared MW-50's fundamental limitation: finite capacity. The largest nitrous oxide tanks held 85 liters, enough for approximately 12 minutes of operation. And like methanol, nitrous oxide was difficult to produce. It required specialized chemical facilities and competed with medical uses. Few Luftwaffe aircraft received GM-1 systems, and those that did often flew missions with empty tanks due to supply shortages. Neither system addressed the root problem. MW-50 and GM-1 were tactical band-aids applied to a strategic wound. They provided brief power increases under specific conditions, but did not fundamentally change the fuel chemistry that limited German engine performance. American pilots still had unlimited access to war emergency power throughout every flight, every mission, every day. German pilots had temporary boost systems that might work for a few minutes if supplies were available and systems functioned properly. Luftwaffe maintenance crews worked exhaustively to keep these systems operational. They scrounged methanol from wherever they could find it. They carefully rationed nitrous oxide supplies. They repaired pumps and plumbing and control mechanisms. But no amount of maintenance effort could overcome the industrial chemistry disparity that made American 100-130 fuel possible in unlimited quantities, while German methanol and nitrous oxide remained perpetually scarce. The knowledge that their fuel was inferior created a psychological burden that Luftwaffe pilots carried into every combat mission after mid-1944. It was not a matter of courage or skill. German fighter pilots in this period were among the most experienced combat aviators in history. Many had flown hundreds of missions. They understood tactics, understood their aircraft, understood how to fight, but they also understood they were fighting with a permanent handicap built into their fuel systems. Every engagement began with the knowledge that American fighters could sustain maximum power longer. Every tactical decision had to account for limited emergency power duration. Every combat calculation included the 3 to 5 minute clock ticking down whenever throttles went forward to emergency settings. Major Gunther Rahl described the psychological impact in post-war interviews. He explained that knowing about the fuel disadvantage changed how pilots thought about combat. Before they understood the fuel disparity, pilots who encountered superior American performance might attribute it to pilot error, to tactical mistakes, to bad luck. They could tell themselves that next time, with better positioning or better tactics, the outcome might differ. After they understood the fuel limitation, that rationalization disappeared. The disadvantage was permanent and inescapable. No tactical brilliance could overcome it. No training could compensate for it. The Americans had more power available whenever they wanted it, and German pilots had to fight while watching chronometers and managing power settings, and accepting that they could not sustain maximum performance as long as their opponents. This knowledge spread through fighter units during the spring and summer of 1944. Experienced pilots explained it to new replacements arriving from flight schools. Technical officers briefed squadrons on the fuel situation. Intelligence summaries documented the American fuel advantage. By autumn 1944, every Luftwaffe fighter pilot in the West knew they were fighting at a fuel disadvantage. The impact on morale was significant but complex. Some pilots became fatalistic, accepting that they were unlikely to survive the war given the material disadvantages they faced. Others became angry at leadership for committing them to combat with inadequate equipment. Still others simply continued flying because orders required it and duty demanded it, regardless of odds or outcomes. Franz Stigler, the Oberleutnant who experienced engine detonation over Western Germany in March 1944, flew combat missions until January 1945. He survived the war with over 500 combat flights logged. In interviews decades later, he recalled the fuel situation as one of the most demoralizing aspects of late war combat. The knowledge that every engagement began at a disadvantage, that the disadvantage could not be overcome through skill or tactics, undermined the fundamental pilot's belief that ability mattered more than equipment. By late 1944, fuel shortages compounded the quality problems. Allied bombing of German synthetic fuel plants reduced production dramatically. The Luna plant near Merseburg, one of Germany's largest synthetic fuel facilities, was bombed repeatedly throughout 1944. Each attack reduced output for weeks or months. By December 1944, German aviation fuel production had dropped to approximately 10% of peak capacity. Luftwaffe units received fuel allocations measured in hours of flying time rather than gallons. Fighter groups might receive enough fuel for 20 hours of operations per week, forcing commanders to carefully ration sorties. Training flights ceased entirely. New pilots arrived at operational squadrons with minimal flight time and no fuel available for additional instruction. They flew their first combat missions with barely adequate skills and no practice time to improve. The combination of inferior fuel quality and inadequate fuel quantity created a death spiral for the Luftwaffe. Pilots flew less, trained less, and fought with equipment disadvantages. Each mission became more dangerous. Casualty rates climbed. Replacement pilots arrived less prepared. The cycle accelerated until, by early 1945, Luftwaffe fighter opposition in the West had largely collapsed despite having aircraft still available. The aviation fuel disparity between Germany and the United States during World War II represents a case study in how industrial capacity determines military outcomes in modern warfare. It was not the most dramatic technological gap of the war. It did not involve revolutionary new weapons or secret scientific breakthroughs. It was simply chemistry, applied at scale, creating a consistent advantage that compounded over thousands of combat engagements. American petroleum refining capacity in 1944 exceeded 5 million barrels per day. Refineries from Texas to California to New Jersey processed crude oil through catalytic crackers, alkylation units, and reforming equipment to produce specialized products, including high-performance aviation fuel. The infrastructure to do this at scale represented decades of industrial development and billions of dollars in capital investment. Germany's synthetic fuel plants, by contrast, represented chemical engineering triumph operating under severe resource constraints. Converting coal into liquid fuels through Fischer-Tropsch synthesis was technically impressive. The fact that Germany sustained any aviation fuel production at all given a lack of petroleum reserves demonstrated remarkable chemical expertise. But expertise could not overcome scale limitations. Even at peak production, German synthetic fuel output was less than 20% American petroleum refining capacity. This disparity manifested in countless small moments throughout the air war over Europe. Every time a German pilot reduced throttle after 3 minutes at emergency power. Every time an American pilot maintained war emergency power for 15 minutes during combat. Every time a Luftwaffe mechanic tried to scrounge methanol for MW-50 systems, while P-51 pilots took unlimited 100-130 fuel for granted. Each moment was small, but multiplied across thousands of aircraft and tens of thousands of sorties, the cumulative effect was decisive. The story began with Oberleutnant Franz Stigler hearing detonation in his engine over Western Germany in March 1944. That moment of realization, when he understood that his fuel limited his combat effectiveness in ways pilot skill could not overcome, reflected a larger truth about the war. Germany was fighting industrial powers with greater resource access, greater production capacity, and greater ability to translate raw materials into military capability. Fuel was just one example. American factories produced 297,000 aircraft during the war, compared to Germany's 119,000. American steel production exceeded 88 million tons annually compared to Germany's 30 million tons. American aluminum production, critical for aircraft manufacturing, was approximately 920,000 tons per year compared to Germany's 250,000 tons. Every material metric showed similar disparities. These numbers determine outcomes more certainly than tactical brilliance or strategic vision. Courage mattered. Training mattered. Leadership mattered. But material superiority, sustained over years of industrial warfare, mattered more. German pilots in late 1944 and 1945 understood this with painful clarity. They continued fighting because duty required it, because orders demanded it, because surrender was not an option, but they knew the war was lost. The fuel disparity offers a lesson that extends beyond World War II. Modern military power rests on industrial foundations that take decades to build. Refineries, chemical plants, manufacturing facilities, transportation networks, skilled workforces. These create capabilities that cannot be improvised during wartime. Nations that possess this industrial depth have options in conflict that nations without it simply do not have. For Franz Stigler, flying his Bf 109 over Germany with C3 fuel in his tanks and 3 minutes of emergency power available, the lesson was immediate and personal. He was fighting the most powerful industrial nation in history, and that nation had given its pilots fuel that allowed unlimited access to maximum power whenever they needed it. No amount of skill or courage could overcome that advantage. The fuel in his tanks told him everything he needed to know about how the war would end. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.